Okay, here we are, grade 10, our last unit of the year. So we're doing energetics and rates, our last chemistry unit. And we'll be having a unit test in this unit. Want to give you guys one more chance to have a good knowledge understanding grade before the end of the year report card. So your last knowledge grade in the whole semester is going to be this unit test. It's a short unit, so hopefully you'll be able to do really well on that test. So today we're going to be talking about energy and chemical reactions, and we're going to just kind of introduce some key concepts to the unit, not start too intensely, and we're just going to setup. So of course we have our title page, Unit 7, Energetics and Rates, May 2nd, start date for the first class, May 3rd for the second class. So add your title page, add your table of contents, so we're doing chemical reactions and with rates. The phenomenon is cyanotype exposure time, and of course the big ideas. If you haven't been doing these table contents throughout the course, it'll be harder to find your stuff when you're reviewing for the final exam. You should already be starting to do. So please, if you haven't been doing them, add them, go through, make ways to mark your notes so you can find the information you need to have to study. Okay, so how can chemical reactions be manipulated? Here is our phenomenon. So that's the phenomenon question. Those are what you notice and wonder, and then what you first think. We're doing this stuff today, and this stuff at the end of the unit as per usual. So go ahead and make your template for this. Pause the video while you do so. Here's our phenomenon. So those of you who are taking art, and we did cyanotype for our first chemistry phenomenon as well. So here we have different cyanotype, different kinds of exposure. So we can see here's the cyanotype, and here it was covered with paper, more or less exposure to light, and kind of compare the two colors of how that affected the development of the chemical reaction, because cyanotype is a chemical reaction here. So we can see the amount of time that the cyanotype was exposed to the sun, and these are from the squid dissection images that were taken. So we have 1 minute exposure up to 8 minutes. Okay, we can see how it's getting darker, and then it starts to get this really nice and crisp image at 4 minutes of exposure, but then it gets too far. Right, so the amount of time you allow the reaction to happen is part of what's going to control this chemical reaction. If you look here, there's not enough time in the sun, not enough time for the chemical reaction to happen. Overexposed, there's too much time, and well exposed, it's perfect amount of time in the sun. There's much more detail in this image because the chemical reaction allowed that to happen. So you want to make sure we can change our chemical reactions based on time and other factors that can affect the reaction rate. So take a minute and put in what you noticed about those images and about doing cyanotype if you've done it. About how exposure time affects it, and make a note of what you first think is the answer to this question: how can chemical reactions be manipulated? Our final lab in this unit is you're going to be planning your own procedure and everything for chemical reaction, so you'll be manipulating a reaction to see how it affects this rate. Right, so next template is, of course, the big ideas. This is the very last light bulb. We don't do big ideas in the IB, so this is the last one, guys, so draw a really beautiful light bulb. And our template for today's actual lesson has, this is where we're going to put a little list of key information here. You have a diagram to draw here and a formula here. So go ahead and draw this. Template, you can see an example in my notebook at the front of the room. And you have a place for calculations. You need to always have a calculator in class for this unit, so make sure you have one ready to go. Okay, so our target for today is I can analyze the energy of chemical reactions through specific heat capacity, and I can use specific vocabulary to describe chemical reactions. We're going to review something from grade 9 chemistry here, and that is physical and chemical properties and changes. So do you remember physical properties from back in grade 9? You don't need to write this down, but be kind of aware. Physical properties are properties that you can be observed or measured without changing the matter's identity. So you can figure out the conductivity, malleability, solubility, density, all those things about a substance without actually changing it in some way. And then a physical change, that goes with physical properties, is where we're going to change the form of the matter, but not its chemical identity. Okay, so these are physical changes in this image here. So we have melting of ice, it's still H2O, it's still water, was a solid and now it's a liquid. Chopping wood in small pieces, it's still the same cellulose molecule. Shredding paper, mixing different colored marbles, these are all physical changes. The chemical identity of those substances hasn't changed even if their physical form has changed in one way or another. So if we were to put sugar in water and mix them together, would that be a chemical change or a physical change? Go ahead and talk to your partner. What do you think? Are we changing the identity? Well, this is going to be a physical change, and the reason for this is because when we dissolve sugar in water, we're not actually creating a new substance. The sugar and water molecules just disperse themselves through diffusion. They don't actually create a new substance. So we can call that this is just dissolving, and the way we can know for sure is we can reverse this. So we can take a physical change. We can take the sugar water, we can boil the water away so the sugar is left. We can separate them back again. What are some other examples of physical changes where you are only changing the properties of a matter but not its chemical identity? You talk anything where you're changing state, if you're heating up a substance and changing it to a gas or from a solid to a liquid, that's definitely going to be a physical change. If you're going to be mixing substances in a way that causes them to dissolve, like salt and water, just like we have sugar and water, that's also going to be a physical change and not a chemical change. Okay? So classic physical changes are going to be states of matter. So where we're changing between a gas, solid, and liquid, but it's still the same chemical substance. These process condensation, evaporation, sublimation from a solid right to a gas, and deposition from a gas to a solid, and melting and freezing. These are all physical changes and are not changing the chemical identity of the substance being involved. The classic example, of course, is water. Now, chemical changes, these ones you need to know because they're a big part of our unit. So what are chemical properties? Do you remember this from grade 9? So chemical properties are going to be ones that you can only observe through a chemical reaction by changing the matter's identity. So for example, reactivity. We mix vinegar and baking soda and we see how much it reacts. That's a chemical reaction, a chemical change, and therefore it is changing the identity of it. Okay? Flammability. What does it burn? If we were to burn it and know how well it burns, that's a chemical change. You can't undo that. Therefore, it's going to be chemical properties. Same thing with acidity, how acidic it is. To test that, you're going to have to mix it and then cause a reaction where it's going to react based on its acidity, and we cannot undo that. So it's also considered a chemical property of matter. So that's what chemical properties are, and therefore, if that's a chemical property, a chemical change, logically, is a change when the particles of a substance are rearranged to make a new substance. So the atoms inside a chemical are going to be rearranged to make a new chemical. And that's what chemical reactions are. We did a lot of imbalances and we're looking at rearranging atoms in our previous chem unit and the second unit in grade 9 science. And now we're going to be building on that and the changes that are happening in reactions and looking at how to control them in different ways. So a really good way to kind of figure out, is this a chemical change or a physical change, which is an important thing for you to be able to do in this unit, is think, can you reverse it? Can you undo that change? Like with the sugar and water, we could just boil the water away and it would go back to being sugar and water. But if we burn some wood, like here we have burning wood, is that a chemical change or a physical change? Well, can you take that wood after it's been burnt and put it back to how it was before? You definitely cannot. Therefore, it must be a chemical change. Okay? Okay, so this is your list of chemical changes. We should write them in the box on your template here. So these are the signs you should memorize these. So a color change, if it changes color, it's definitely going to be a chemical change as long as it's a true color change. So for example, if you mix a red liquid and a blue liquid and it gives you a purple liquid, that is not a color change. That's just blue plus red equals purple. Okay? If you mix like a clear liquid and a blue liquid and makes a light blue liquid, also not a color change. It has to be a significant change that's not just from mixing colors the way you might do with paint in art class. Okay. A change in temperature. This one is bolded. It's a big one for this unit. We're going to measure change in temperature a lot. to measure the energy of chemical reactions. This is a really important one for us to analyze in this unit. How much if there's being light produced by the reaction, that's on a chemical change. If there is a gas or an odor being produced, so you can see bubbles of gas, or you can see an actual smell being produced also from a gas, those are signs of a chemical change. If there's a solid precipitate, and a precipitate means you're mixing two liquids and you create a solid. So oftentimes it sits kind of at the bottom of a test tube full of liquid. You have a bit of solid accumulating, and that's called a precipitate. We'll see that in this unit for sure. And the last one, it's difficult or impossible to reverse. So like turning that burned wood back again, that is some of the chemical change. We can't really do that. We can't turn it back to regular wood. Okay, so I'm going to show you a little video here of an example, and I want you to figure out if it's a chemical or physical change. Okay, so that reaction, that is two clear liquids forming a yellow solution. So it's a color change, and it's also a precipitate. You can see how the yellow was actually a powder dissolved in the water, so that makes it a solid. It's a precipitate inside of two liquids. So we have two signs of a chemical change, therefore that is a chemical reaction. Okay, write down your first big idea of this unit. How does the conservation of energy within systems explain the processes of chemical reactions? And this is your first kind of real draw me. So your only drawing for today is you need to draw these two boxes, the arrows coming in and out, delta H and greater or less than 0, and the names. We'll see what those look like in a second and we'll explain them. But those are your drawings for this lesson. Please look at my example notebook if you need to see an example of what it would look like to draw these correctly. So when chemicals react, they're going to cause a release of energy changes. Okay, so the energy is going to be changed somehow during a chemical reaction. What kind of examples can we think of this happening? So back to our like burning of wood, that's releasing energy in terms of light and heat. The one we just looked at, we have changing of energy in terms of producing different kinds of chemical bonds, creating bonds and breaking bonds. That all requires energy. A change in temperature, simply for producing of heat through combustion, through burning things, is a very, very good example of this. And the way to understand how energy is changing when chemical reactions happening is to think about how chemical bonds are formed, how they're made, how they're broken, and how changes in bonds are going to affect energy. So we're going to do something called bond enthalpy in this unit and look at the energy in chemical bonds and how much energy is released when they're broken, how much energy is used to make them, that kind of stuff. So there's two main types of reactions we're talking about in terms of energy. We have exothermic reactions, and this is the most common type. The most common kind of reaction is exothermic, and you can see that in the first image here. It's a blue box, exothermic, because what's happening is it's going to be releasing heat to the environment. So it's getting cooler in the system. The box represents the system. Could be like the test tube where the reactants are happening, and because it's going to be losing heat to the surroundings, it's exothermic because the prefix X means leaving, okay, or outside. So from the system in the blue box to the surroundings. And that means the delta H value is less than 0. We will talk about what delta H means later. So for right now, just write it down and it'll make more sense to you later on in the unit. That's an exothermic reaction. Temperature goes up of the surroundings and it goes down of the system because it's losing energy to the surroundings. If that's exothermic, think a minute, what could endothermic be? The other image here, the red one. Well, endothermic is going to be the exact opposite. In an endothermic reaction, the heat is going to go into the system. So the surroundings get cooler and the system gets warmer, and therefore delta H is greater than 0. So exothermic, so endo means inside, exo means outside. So energy is going outside in exothermic, energy is coming inside endothermic. And that energy we're talking about is thermal energy, it is heat energy. So a lot of thermometers to collect data in the first part of this unit. Okay, once you have that written down, we're going to continue on here. So a great way to think about this is looking at a positive or negative change in energy. Okay? So which one do you think is positive and which one do you think is negative, and why? Take a minute, pause the video, talk to a deskmate. Why do you think which one's positive? Endothermic, exothermic, which one's negative, and why do we think that's the case? So exothermic are negative energy changes because they're losing energy in terms of the system where the energy was. It's leaving the system. This has less energy afterwards, and therefore it is negative. An example here is where we're going to have magnesium ribbon and hydrochloric acid reacting in this cup. They're going to lose energy, temperature is going to go up the system, so it's exothermic. Endothermic, we have positive energy changes. Okay, so that's where we're going to be the energy is leaving the system and going to the environment, and they're taking in energy into the system. So energy is coming into the system from the environment. Okay, example here is sodium hydrogen carbonate and hydrochloric acid reacting here. The temperature is going to go down in the system because we have energy being brought inside the system. Okay, so energy, the environment is going down because we're heating up the system inside. The energy is coming inside the system. Now these are both placed in styrofoam cups, and the reason why we always use good insulation in terms of these energy reactions is because we want to maintain the heat inside so we can track it better and we can see the changes. We don't want to lose heat to the environment because we don't know where the heat's going. We want to have more control on that. So this is what we do to help us do that, is we make sure that we keep the heat in as close as possibly can by doing an insulated thing like a styrofoam cup, or 2 styrofoam cups, in fact. Okay, now important to know here, the law of conservation of energy. We talked about this before in physics and chemistry. It's an important idea, like the law of conservation of matter, same kind of idea. But in this case, it's not about matter, it's about energy. Energy cannot be created or destroyed. Every single branch of science uses this. Okay? Now, we know energy can change forms very, very often. We see a lot of energy changing forms. Think about photosynthesis. In biology, we have sunlight energy turning into chemical energy in glucose. Okay? So think about physics. We talked about like collisions happening. So we have different kinds of kinetic energy changing forms. So all science uses this kind of energy analysis. So in chemistry, important ones are going to be potential energy, the energy that's stored inside chemical bonds and inside the nuclei of atoms that hasn't done any work yet but could do work. Then we have kinetic energy, the movement energy of particles. We often talk about that as thermal energy because movement of particles does generate heat. And this is as a way to measure, so temperature really is the average kinetic energy of the particles inside of a substance. So if we look here, the temperature, the one that's moving the most is going to be the one with the highest temperature, right? Particles move more because it's hotter, so the kinetic energy of the particles moving is also related directly to temperature. They are directly proportional. Okay, so when the temperature is of 2 systems that are near to each other, when they are different, the energy will change between them until they reach a thermal equilibrium, until the temperature is the same everywhere. So we can see what's happening is we have these high temperature particles and these low temperature ones, so like air molecules, because they have big arrows on them. Over time, the heat's going to transfer from here to here, and we'll end up having an equal heat energy everywhere in the both systems. As long as the molecules can move between the systems, there's no insulation, no separation, this can happen. There is a similar tendency to pressure and concentration equilibriums. Same thing happening, pressure going to an equal place, concentration going to an equal place. This covers about heat transfer as a way to reach thermal equilibrium, a balance between temperatures. Okay, so that's the theory stuff for today. What we're going to go into now is actually applying this with our very first formula in this unit. So we're going to talk about specific heat capacity, and this is your formula you need to draw in your last little box, Q equals mc delta T. Make sure you define what those variables are, as well as the units, because you'll need to have that. Like in our other chem unit and physics, you will have a formula sheet for this, for your quiz, test, and for the final exam. So you need to know how to use the formula, what the variables represent, but I will provide them to you for the test and quiz. So heat capacity is the amount of thermal energy needed to change the temperature of a system by 1 degree. And this depends on the material of a substance and its mass. So we can use those as ways to kind of change the heat capacity of a system. The specific heat capacity, represented by the variable C, the symbol C, is the unit per, so heat capacity per unit mass based on the formula. So if you look at this formula, what kind of relationships can we infer? What kind of patterns can we see from a formula? Well, hopefully we can see that if we're going to increase the mass, everything here is directly proportional, nothing being divided. So if we increase mass, we're going to increase the energy transfer. If we increase heat capacity, we're going to also increase energy transfer. If we increase the change in temperature, we're going to also change the energy transfer. So everything is directly proportional. You increase anything, it's going to increase everything else. They're all related to each other. Looking at this table here and these heat capacities, which one do you think is going to heat up the quickest, and why do you think that? So the quickest substance to heat up is going to be the one with the smallest heat capacity. So the smallest amount of energy, or joules, per gram per degrees Kelvin to change temperature. So the one that's going to be the quickest to heat up is going to be gold, because it takes the least amount of energy to change its temperature, and the slowest is going to be water. We already know water has a high heat capacity from our properties of water, talking about it for climate, talking about it for Earth's air and water last year. Hydrogen bonds, all that stuff. Now we're bringing into chemistry. If you want to cook food really fast, what would you use? Aluminum, iron, copper, or gold, and why? Hopefully you chose gold. It's going to heat really quickly, but you got to be careful because it could just melt and might burn your food anyway. This is why we don't use gold for pots and pans, not just because it's super expensive. So that's heat capacity. Let's try it. Some practice problems. So here's 3 questions. Okay, so you have the materials, which you look at the units and do your conversions, and go ahead and do the calculations. Pause the video, do your practice problems. We'll go through them together in a second. Okay, so at this point you should have done the problems. So number 1, okay, here's number 1. We have our answer here, 7,875 joules. Okay, so we did it. Q equals mc delta T. We put our numbers in, 1.5 kilos times 750 joules per kilogram per degree Celsius times 7 degrees Celsius gives me 7,875 joules. Number 2, my answer is 209,050 joules. So again, I put the numbers in, I multiply them all, there's my answer, boom. In the last one, this one's a little tricky to find the mass, to rearrange our formula here. So the answer is 0.00045 kilograms. So Q equals mc delta T. I put my numbers in, 46.7 joules equals m times the heat capacity times the change in temperature. If I solve that for 0.00449 kilograms. All right, that's the lesson for today. You're going to practice using this format a little bit more. So if you go into there's 10 practice questions for the heat capacity worksheet on Schoology. You need to do the first two. We already did the first two easy ones and the first medium one. Do at least 5 medium ones and then 5 more from any level of your choice. With medium is easy for you, then I would go even harder, okay, and just increase the complexity. That is our first lesson of the unit. Have fun doing the math, and I'll see you guys later. Take care.